Welcome to midpoint Riemann sum. So a midpoint Riemann uses the midpoint of the rectangles and places them along the curve to find the area. The equation that's used for midpoint Riemann sum always begins with f of x to the 1/2, f of x 1/2. That means it doesn't start with the first value. It doesn't start with the beginning. It doesn't start after a change in x. It starts with half a change in x and ends with the value that would be half a change in x from the endpoint. All right, so let's see what that looks like. So instead of taking the value on the right-hand side or the left-hand side, it's the one in the middle. And let's wait for our page to turn ever so patiently. All right, so remember for midpoint Riemann sum, we're using not the first value, not the second value, but the value in between those. And the value in between the second and third values. And the value in between the third and fourth, and so forth. All right? So, given this problem, all we need to note in order to find the area under the curve using a Riemann sum, of course you need to know the function. Right? Either you need a curve, you need an equation, or you need values to work with. You need to know the interval, right? Where are the two endpoints? And then you need to know the number of subintervals, right? So that's the only thing you ever need to know. All right, so let's do a couple of these together. And I'm going to do these right from the beginning, right, including drawing the graph. So we have y equals x cubed from 0 to 4 and 4 subintervals. Right, so if you remember that it looks sort of like an S, right? But I don't need the whole S, right? I just need the part of the S over here. But if you want, here, I'll just draw the whole S. Right, and you're not caring how well you draw it, right? Because you're only caring about what the values are, right? That's just so that you can have everything shown out and diagram it out, know what values you're using, but not because this is a great graph. Right? And so the starting value is 0. Right? So we're starting right at 0, and we're going to go to 4. Right? So I'm going to make these kind of wide. 1, 2, 3, 4. And you know what? That's just a really bad graph, because how high am I going to have to go up on the board? So maybe draw your values on the bottom first, then draw the graph, so that, because nobody cares how well this is drawn to scale, right? This is just a representation, and I don't even need this part, right? Maybe that helps you draw a nice little S, but we don't need that part. All right, so now we need to figure out our change in x so that we can draw the bars, right? So the change in x is just the ending value 4 minus the starting value 0 divided by the number of subintervals, so that's 1. Right? So each of my subintervals is going to be 1 unit long, but we're not starting at 0. That would be a left Riemann sum. We're not starting at 1. That would be a right Riemann sum. We're starting at the value that is halfway in between 0 and 1, which is 1/2. So we're going to use 1/2, 3/2. So notice I'm putting in the values that are between the what I would use for a right Riemann sum or a left Riemann sum. So 1/2, 3/2, 5/2, 7/2. Right? And so our bar is going to go to where that hits the curve. Right? So there's our bar, drawn as best as I can, where 3/2 hits the curve, where 5/2 hits the curve, and then where 7/2 hits the curve. But I don't have to worry about how well this is drawn to scale, right? This just makes sure that I understand, okay, these are the values I'm using. Yep, that's the midpoint. I got it. I'm going to plug in 1/2, 3/2, 5/2, and 7/2 into the equation. All right, so we have, I'm going to switch colors here. F of 1/2 would be 1/2 cubed, which is 1/8. F of 3/2 is 3 halves cubed, which is 27/8. Well, one nice thing, they're going to have a common denominator. So that's one thing I don't have to do. F of 5 halves, and by the way, these are all in your notes. I think a couple of the notes are a little out of sequence, or I shouldn't say all of them in your notes. Many of these problems are in your notes. Just look for them. Right? F of 5 halves would be 5 halves squared, which is 5 halves cubed. I take a break to say something, and then I write in a wrong exponent. Of course, I realized it like instantaneously. That would be 125/8. And f of 7 halves is 7 halves cubed, which is 343/8. So our sum, we're going to take the change in x, which is 1. Now, I write that in even if it's 1. I would do that on the AP exam, because this shows you know to multiply by the change in x, right? You don't want them to have to figure something out, because they may not err in your favor, all right? So make it clear, all right? And chances are the change of x isn't going to be 1 anyway. But 1, and then we add up the values, right? So we add the 1/8, the 27/8, because these are all the heights of the rectangles, right? So all of these f of x's is the heights of each of the rectangles. The width of all the width of all the rectangles is the change in x. And we know the area of a rectangle is height times width, or width times height. So that makes the area under the curve here equal to all the f of x's, right, times the change in x. Not written down. This isn't the most perfect notation, right, because that may make people think, oh, maybe it's just one f of x, right, but this is all the f of x's. So I'm just going to put a little thing underneath here, all of the f of x's. Right? We take all of the f of x's, right, and multiply that by the change in x, right? And that gives you height times width. So we find the area of a curve as a rectangle. So let's continue on with this. This might be a good thing, by the way, to put in the notes to really make that clear what we're doing. We're not just adding up some values of the function. We're literally adding up areas of rectangles. So 1/8, 27/8, because it's not, I mean, the work is kind of easy, but maybe the concept isn't completely easy, until you really make sense of it. All right, so of course I'm not going to really bother with the 1. And now we're just going to add up all of those. And to make it a little faster, I do have didn't have to use a calculator until now, but I can do probably a little faster. 343, 125, 27. So 496/8. Well, that's definitely reducible. I wonder if 496 is divisible by 8. It is, 62. So the sum of the area under the curve is 62. And this is a pretty good approximation because we used a midpoint Riemann sum. So you can see there's some parts of the curve we're missing, like noticeably right here. And obviously it's not drawn to scale. And then you can see there's some parts where I overlapped, right? I went over the curve, but that's okay, right? And it is what it is, right? This is an estimation, an approximation. All right, so now let's find another one. And, all right, so now let's do a midpoint Riemann sum. All right, so we're using half the change in x, right, and the width of our rectangles is a change in x, right? But we use that value in between. So this is 1 over x squared. I remember I erased this. This was a really interesting graph. I'm going to try to make sure I've got enough room here. 1 through 6. All right, so I'm going to draw the number line first. So 1, 2, 3, 4, 5, 6. All right, so no matter what, this is the value of the function is going to be positive, right? Because no matter what number I plug in, I'm going to have a positive number. So this particular graph sort of looks like this. It does have a, there's a good reason 0 is not used. It's got a vertical asymptote at 0, all right, and it's decreasing, right? Because if you divide 1 by greater and greater numbers, you get less and less, right? This is actually what's called a converging function because it heads to 0. It converges to a value, as opposed to a divergent function, which just keeps on growing. All right, so that's kind of basically what the graph looks like. So we're going to use, I hope I left enough space there. We're not going to use 1. We're not going to use 1/2, of course, 2. We're going to use halfway points. And actually, let's make sure, actually, we're not going to use 1 or 2, or 1/2, because look how many subintervals. Before you start drawing any bars in, it's okay to draw the function. All right, so it was okay for me to put the numbers there. But before I do anything else, we better find change in x, because it ain't 1. All right, so we have 6 minus 1 divided by 10. That's 5 divided by 10. That's 1/2. So ooh, I wish I kind of made this a little bit bigger here. All right, so let's see what we can do. All right, so here is 1/2, and I'm just going to start these numbers again. Now I remember why it was an interesting graph. I have to shove the values in. All right, so we have 1, and then we don't want, and then this is going to be 1/2. So I'm going to put these values in because our bars are going to be between 1 and 1/2, because the bars are 1/2 long. All right, the midpoint uses the halfway point. So guess what we're using? Not 3/2. No, we're using the halfway point between 1 and 3/2. We're using 3/4. All right, so 3/2, 2, and 5/2. So I'm going to make a suggestion. I'm just kind of that person who always wants to put the numbers on the graph first. Don't do that. Just because you may have to erase it when you realize, whoops, I need to really squeeze a lot of numbers in here. So I better make sure I got enough room. So 7/2, 4, and 9/2, and 5, and 11/2, and we can just squeeze in 6. Kind of off the screen there. All right, so this was what the difficult part was, squeezing in all these bars. All right, so now we're starting off at 1. That's why I didn't mind if I crammed in the 1/2 there. But we're not using 1. We're not using 3/2. We're using 3/4. And the bar is going to be 1/2 long. Now, I don't know if I can honestly squeeze in those numbers, those halfway points in between. So how about I put them up here? So we're going to find f of 3/4. I don't think I can squeeze it in between. So we don't want 3/2, we don't want 2, we want the halfway point. All right, so that would be, so now here's an easy way to figure out, because after a while you're like, okay, what's between 3/2 and 2? All right, they're going to go up by 1/2 each time. All right, so 3/4 plus 2/4, oh, that's 5/4. So the next one, of course, would be 7/4, right, because the widths of these are 1/2. All right, so here we go. So we go to the midpoint there, and this is f of 7/4. And this would be 9/4. Oops. And this would be f of 11/4. And f of 13/4. And f of, well, I take it back about me being able to squeeze in the numbers. How about I write them down here? F of 3/4, f of 5/4, f of 7/4, because you can't even read them anymore. F of 9/4, F of 11/4, F of 13/4. All right, we'll continue. And then I'm going to just move these because this just looks like, oops. Oh, no, I'm not going to move them. There go my bars. I'm just going to erase them because I can't even read them. I almost left it up here. I already had this done. I'm like, I can leave it up here and just go over it and I wouldn't have to write it again. And I'm like, no, I better go over it so they understand it. And you see, sometimes you have to fix things, like realizing there's not enough space to write those numbers up there. All right, so now I need the next bar. It's going to be halfway between. All right, so where I'm measuring is the halfway point. The bar's width is 1/2 because that's the change in x. The place where I'm measuring is halfway, though, between the two endpoints. So between 9/2 and 5, I just add 2/4. So that'd be easiest, 15/4. And I can just check at the end, make sure I didn't go over 6. Right? And then halfway in between that bar, because that's a half, and we want it to be a half, but we want to measure at the midway between an integer and 1/2 more. So that would be F of 17/4, and then one last bar, and something seems amiss. Did I on my numbers? Did I start in the? Oh, I started in the wrong. Oh man, I don't want to do the video again. Not 3/4. 3/4 would be halfway between 1/2 and 1. F of 5/4. No problem. Now all the others. So take out the 3/4. Were you thinking about that? Were you like, no, F of 3/4 is between the 1/2 and the 1. We aren't using that value. That's not in the interval. I shouldn't have even written the 1/2 in there. I just did it just to be consistent. So it's now you can see what to do just to check yourself. So when I got to the last one there, I'm like, okay, no. 19/4 is less than 5. That's not good. All right, let's see, where did we go wrong? Did I miss one? Did I count wrong? Did I put the same one twice? No, I started too soon. So not 3/4. 3/4 is not in between 1 and 3/2. 5/4, right? It has to be more than 1. All right, so 15/4, 17/4, and 19/4, and then one more after that. And there should, by the way, be 10 values here, right? Because there are 10 subintervals. 1, 2, 3, 4, 5, 6, 7. So we got 8. And then right here, in between 5 and 11/2 would be F of, man, these don't want to fit in here, 21/4. Well, I'm giving you time to write, aren't I? And I'm going to go through where all the bars are located. 21/4 because I couldn't fit things on there. And I'm out of space. So let's put it over here, the last bar, which would be F of 23/4. Now, let's see if that's the right number of bars. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 subintervals. That's good. Is 23/4. So 5/4 is greater than 1. We can agree there. 23/4 is less than 6. Good. We stayed in our interval. And halfway between 1 and 1.5 is 1 1/4. 5/4 is 1 1/4. Each of our bars is 1/2 long, so I don't have to keep figuring out what's halfway between 3/2 and 2. And that's 6/4 and 8/4. That would be 7/4. But that gets a little tiring. So after you've figured out 1 or 2, you can say, well, the width of the bar is 1/2. I can count up by 1/2. So 5/4, 7/4, 9/4, 11/4, 13/4, 15/4, 17/4, 19/4, 21/4, 23/4. Each time I counted by half, and then they correspond with these halfway points that are right here. So they correspond with that value, that value, that value, that value, that value. This is, by the way, this is the hardest one on this whole page. or this whole video, is this one right here, because it had a lot of subintervals jammed in there. Now I know why, when I looked at my notes, why I had yellow lines in there, so I could go over them and explain them again. I probably did the same thing a year ago. So now let's plug these into the function. All right, so this would be 1 over 5/4 squared. So we're going to square it and we're going to flip it, right? Because this is going to, if you're dividing by a fraction, you're multiplying by the reciprocal. So this is going to be 16/25. And this is going to be, and lucky for us, we don't have any like denominators, do we? So this is going to be 16, we got like numerators, 16/49. And this one, oops, let's write the square in there, is going to be 1 over 9/4 squared. That's going to be 1681. So notice the numerator's not changing, just the denominator each time. Oh, joy. 1 over 11/4 squared is going to be 16 121s. 121st. 1 over 13/4 squared is going to be 16 169ths. This one would be 1 over 15/4 squared, which would be 16 225ths. Come on, we're waiting. Didn't I draw on the rest? There we go. 16 225ths. 1 over 17/4 squared is 16 289ths. This one is 1 over 17/4 squared. That one is, oh, what is 19 squared? It's 300 and something. It's not 381. I don't think that's right. Well, let's find out. 361. I was close. You don't often come up with, need 19 squared. All right, so, oops, that's a 19. Oop. This one is 16 361s. The next one is 1 over 21/4 squared. That one is 16 441. And then 1 over 23/4 squared is, I don't know, 23 squared, 5/29. I would not have guessed that. 5/29. Excuse me, 16 5/29. Oh, well, I take that back. 21 squared would have some 3s in it. So, but to come up with, to try and factor all that and figure out what would be the common, I may as well just say, forget it, the common denominator is just going to be the product of all those. Because the only one that has something in common, well, 15's got a 3. 15 squared. 21 squared's got a 3. Well, all right, so I could probably leave the 9 squared, one factor of 9 out, but by the time I figure that out, it would probably be less work for us just to multiply all those denominators together, and then we will reduce at the end. So I got 25 times 49 times 81 times 121 times 169, oops, times 225 times 289 times 361 times 441 times 529. Oh my. I'm wondering if I had this up from last year, because this is a horrible number. Well, you know what? You can do this, by the way, on the AP test, what I'm going to do now. That common denominator is so horrible. I'm just going to do this. 1/2 times 16/25 plus 16/49 plus 16/81 plus 16/121 plus 16/169 plus 16/225 plus 16/289. Let's see if we can squeeze it a little bit closer. Come on, move over, move over, move over. Everybody move over. Otherwise I have to do two lines. Plus 16/361 plus 16/441 plus 16/529. And there we go. We're done. You don't have to, it's just simplify. Now, for me, simplify, because I won't give you one like looks like this. But you actually don't have to simplify in an AP test. If you show the sum and you leave it like this, ooh, it will be good enough. Man, I just separated all my things out. So I'm just going to squeeze the 1/2 in there, and there we go. There is the area under the curve is approximate. The area under the curve. Area under curve approximation. I'm going to have to look at last year's and see if I actually took the time to find that denominator, because it gave me a horrible answer. I have a feeling I didn't. So we're done with this one. Let's move on to the next one. And by the way, if you have any questions on these, just let me know. Boy, that was a tough one. Now I remember why that was such a tough one. These ones are already kind of written in, and if they're in your notes, they're already written in. The only thing I'm going to do, I left this as fractions. I would work with fractions as opposed to decimals. It's a lot easier to work with them, and then you don't have to worry you rounded too much. By the way, 3 decimal places. That is bad rounding, and this was an AP. This was from an AP site from a long time ago. They want more than 3 decimal places, so I would stick safer with at least 4 decimal places. But anyway, find the area y equals x squared, and find the area between y equals x squared and the x-axis, between 0 and 1, using Riemann sums in 4 partitions. So the change in x, you just take the ending value minus the starting value and divide by the number of partitions. So each one is going to be 1/4. Right? So this one is a left Riemann sum. Right? So it didn't say it up there. You're left to wonder. But down here it tells you, well, we're going to use a left Riemann sum. So that means we're going to use the left-hand side of the curve. I'll write in something. So that, I'll write in green here. So that would be 0 over here. Right? That's the left side. Each of these is a width of 1/4. So then it would be the starting value plus 1 change in x, plus 2 change in x, plus 3 change in x. Those are the values we would use. We would not use the 1, right, because that is for the last values for the right Riemann sum. So we use the starting value and we go up by a change in x. So when we plug it in, we would have our change. So to find the left Riemann sum, or the left rectangular articulation method, whichever one you want to call it. I like Riemann sum, left Riemann sum. It would be the change in x times all of the heights for the 4 rectangles. So we're using f of 0 plus f of 1/4 plus f of 1/2 plus f of 3/4. All right, so when you plug that in, f of 0 is 0. F of 1/4, 1/4 squared is 1/16. F of 1/2 is 1/4. So I just changed that from 1/4 to 4/16 so I could add it, because it was the only one that had a different denominator. And then the last value is f of 3/4, which is 9/16. Add them together and you have 1/4 times 14/16. you can reduce, and 730 seconds is our answer there. And that's the exact answer. And I would stick with exact answers whenever possible. It asks whether this is an overestimate or an underestimate. This is an underestimate. You're always going to have an underestimate when you have a left, and make sure you know this, a left Riemann sum and an increasing function. They could also, if it's an increasing function, it's also concave up. So that's another way to put it. All right, so left Riemann sum, and it's increasing is concave up function there. We're going to end up being an estimate, right? Because the right-hand value is bigger than the left-hand value. All right, I think I have the same problem, only with the right Riemann sum. And I am right. All right, so exact same change in x, because it's the same interval and the same number of partitions, but I did write it again. Right, so 1 minus 0 divided by 4, 1/4 is the change in x. This time we're using not the left-hand side, but the right-hand side. So we're not starting with 0. We're starting with 0 plus a change in x. So 1/4, which is the right-hand side of that rectangle, because each of those rectangles is 1/4 in width. And then 1/4 plus another change in x, which would be 1/4 plus 1/4, which is a half. 1/2 plus another fourth would give you 3/4, and 3/4 plus another fourth is 1. So notice on this, we're always using the right-hand side of the rectangle. This is n. So let's look at the sum, and then we'll talk about overestimate, underestimate. All right, so you're not going to plug in 0, but you're going to plug in the 1/4, the 1/2, and the 3/4, just like as you did on the left Riemann sum. But now you're going to plug in f of 1 instead. So, and we multiply that by the change in x. So we have 1/4 times 1/4 squared would be 1/16. 1/2 squared was 4/16. 3/4 squared is 9/16. Of course, 1 squared was 1, but we made that 16/16, so we can add it together, which gave us, looks like it says 30/16. And then we can multiply by reduce and multiply by the change in x, and that gives us 1530 seconds. All right. This one is an overestimate because this is a right Riemann sum. And an increasing or a concave up function. Okay. All right, so now same problem, only now it's a midpoint Riemann sum. All right, so now we're not using the 0. We're not using the 1/4. We're using halfway in between. And I think I'll draw these in for you while I'm going over it. Oops, we also lost our function. That's right. So there we go. Good enough. All right, so we want the value halfway. So we're not using the 0, which we'd use for the left Riemann sum. We're not using the 1/4, what we'd use for the right Riemann sum, because the bars are all 1/4 in width. Right? We're going to take that change in x and divide by 2, and that's what you're going to use for your midpoint Riemann sum, or midpoint rectangular approximating method. There we go. So our bars are still going to be 1/4 in length. However, we're going to use the halfway point. So half of the change in x divided by 2 is 1/8. So we're going to plug in here 1/8. And halfway between 1/8 and 1/2, not going to mess this up this time, it's going to be 3/8. And once I know my starting value, I can count up by my change in x. So it's 1/4 or 2/8. And then halfway between 1/2 and 3/4 is going to be 5/8. Oh, I didn't draw that curve very well. Here. I shouldn't have erased it. I didn't realize I had drawn that in, because I got to hit my bars. Otherwise, it's not very, I have to draw new bars. Okay, and then that's better. That's why you draw the function first. There we go. Good enough. Right, and that would be 5/8, and then here, halfway between 3/4 and 1, right? Going up by 1/4 each time, this would be 7/8. All right, and then that's what you plug in. So we plug in, we multiply the change in x, which is the width of the bar, times the heights of all the bars. So f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. Right? And when you plug those in, you get the value, what's written up above there. 1/64, 9/64, 25/64, 49/64, which is 84/64, which we could reduce to 21/16. And when we multiply that times the change in x, we get 21/64. All right, and that's the midpoint Riemann sum. All right, so hopefully that clears up some things on midpoint Riemann sum. The last thing here is just a little review of what values you use in a left. Oh, I have one more. Never mind. I have one more, and then I have a little review, I think. Comes after this. All right, so midpoint Riemann sum. This is another fun one. X cubed plus 1. So it's the same thing. It's the same SE shape, right? But now it's shifted up 1. So let's see. Let's actually, let's find the change in x. So I'll make sure I make it big enough. All right, so change in x would be 3 minus 0 divided by 6, so 1/2. All right, and we're starting at 0, so I can put the values in now. 0, and then 1/2, and 1, and 3/2, and how far do I have to go to 3? And 2, I should have made this longer. No problem. Look at that, it's magic. Don't give yourself much space on the negative side. It's never over there anyway. 5/2 and 3. Give yourself lots of space on the positive side. All right, so it's going to be shifted up. So it's not going to be 0, 0. It's going to be here at 1. So let's see if I can make that look decent. Yeah, good enough. Actually, I think I missed the 3. Got to go out a little wider. All right, there we go. All right, so the one thing we know, so it looks like this if I want to draw the other half in, although not really very well drawn to scale there. All right, so, and some of this, so I would ask, we'll go over this one, whether it's going to be an overestimate or actually, we won't do that on the midpoint. We do that on the left and the right. Kind of hard to tell. So I'll never ask you to figure out if it's an overestimate on the midpoint. You're not going to be able to tell that. But on the left-hand Riemann sum, this would be an underestimate because it is an increasing function. Right? It's concave up from 0 to 3. We know that it's an S, right? This would be an overestimate on the right Riemann sum, but the midpoint's a lot closer. But you can't really tell whether it's going to be an overestimate or an underestimate. So you'll never be asked that on the midpoint. All right, so our bars are going to be 1/2 in length, but we're going to use the halfway point, which means we're going to use 1/4. I think I could squeeze it down there. So here's our bar, 1/2 in width, and the value that we're using is 1/4. And then the next value, of course, is 3/4, because they have to be 1/2 away from one another. And then, could it be 5/4? It could. Halfway between 3/2 and 2, that would be 7/4, right? Because 2 would be 8/4. And 3/2 is 6/4. So this one must be, there we go, 7/4. And then 9/4. Oops, well, you know where it's supposed to be, 9/4. And then the last bar there, we're using 11/4, right? And which is 1/4 less than 3, which is what it should be. All right, so now we'll plug that in. This will be much nicer than that one problem where I couldn't even get a common denominator. All right, so f of 1/4 is going to be 1/4 cubed plus 1. So that's going to be 1/64 plus 64, 65 64ths. F of, this one we have 6 of them too. Not like that other one where we had 10. F of 3/4 would be 3/4 cubed plus 1. All right, so it's going to be 64 on the bottom again. But it's going to be 64, right, for the 1. And then 3 cubed is 27. So 64 and 27 is 81. Oops. 91. 91. F of 5/4 would be 5/4 cubed plus 1. What can I use? Small problems. All right, 125 plus another 64. That's 169. Right? $189. Oops, I keep losing numbers here. 189. 64. And then f of 7/4 would be 7/4 cubed. So that's going to be 343. Oops. $343 and then plus another 64. 407. 64ths. And then almost done. F of 9/4. 9/4 cubed plus 1. I think 9 cubed is 729 plus 64. $793. 64ths. And then 11/4. I don't know what 11 cubed is. Oops. It's whatever 11 cubed is plus 64 for the 1. All right, so 11 cubed, 13. Oh, that's like a palindrome. It's same forwards and backwards, which I guess makes sense. 1331 plus 64 is 1395. Then let's find our sum. So 1/2 times, and we'll add these because we had a common denominator. There's no reason we shouldn't. 65 64ths, 91 64ths, and I have a calculator. 189 64ths, 407 64ths, 793 64ths, 1395 64ths is. Right, so plus 793 plus 407 plus 189 plus 91 plus 65. And then time, so that's 2940. By the way, I wouldn't even bother if this were the AP test because you wouldn't want to accidentally make a mistake. But you know, in everyday work, you should. So we could reduce that. I wonder if it's divisible. It's divisible by 2, I'm sure. Okay, it's divisible by 4. That's probably it, because now it's 735. So 735, so I divided by 4, so that would be 16 times 2. That would be 32. And there we are. We're done with this one. So other than an awful lot of computation, and making sure you use the right values and representing it with a graph, they're really not that difficult. I mean, these are the steps. And mostly the toughest part is computation. And then, if I give you easy numbers, like on some of the other ones, well, then they're pretty easy. If they're whole numbers, oh my gosh, it's easy. All right, so one little note. The midpoint Riemann sum is not the average of the left and the right. The x used for the midpoint Riemann sum is the average of the x used for the left and the x used for the right, but not the sum. Do not add them together and divide by 2. That is just so incredibly wrong. All right, you'd get 0 points for that. All right, use the x value that's halfway between and plug that in. All right, and that's the midpoint Riemann sum, and that's also the end of this video. So I'm going to stop here, and then we're going to be looking at some real-world problems and we're using some tables in the next video. So bye for now.